I'm Senator Al Gore from Tennessee, and I serve as chairman of the Senate Subcommittee on Science, Technology, and Space. I've been actively involved in efforts to make it easier for computers and researchers clustered around computers to communicate with each other much more effectively. Siggraph 89 is going to feature a demonstration using satellite technology that will show what it might be like to have a high-speed fiber optic link between advanced computers in two different geographic locations. Siggraph 89 is one of the few occasions where the experts in this field get together to communicate with the rest of the country about how important these new developments are. They represent, in my view, one of the real keys to America's future.
Welcome to Science by Satellite. I'm Larry Smart, Director of the National Center for Supercomputing Applications at the University of Illinois. Now, I think some of the most important words that Senator Gore was talking about are those involving collaboration. What we really have to do is eliminate distance between individuals who care to interact in a collaborative fashion, not only with other people, but with other computers. Now, we've worked at NCSA with Sun Microsystems and AT&T to put together this demonstration, and Siggraph has been very helpful in allowing us to use this conference, and in particular you, as a part of this historic experiment. Now, Bill Wolf at the NSF has talked about a national collaboratory that will emerge as the video, computer, and communication technologies merge. And this is really a glimpse into that future. Bob Haber is a professor of theoretical applied mechanics and head of the Rivers program at NCSA. And it was really Bob's idea to put this together. And so, Bob, I'd like if you could show us a little bit about the actual technical configuration we'll be seeing tonight.
Okay, sure. On the other side of the stage are a couple of Sun workstations, which are now part of the routine of scientists or computational scientists' daily life. The window desktop environment that's so familiar is an excellent interface into the computational simulations. The configuration slide behind me represents, the red box represents one of those workstations you see on the other side of the stage. Tonight, those workstations have in them the new Sun video board, which allows you to put up live video animation in a window on the workstation screen. And we have the satellite dish outside this building as the source that's going to be feeding that video window. And we're also going to be communicating back to Illinois, back home, via 9600 baud phone line. Just modems, pretty standard technology there. Now, workstations are great, but occasionally we do run into problems that require hundreds of times more power. And over here, we have a diagram of the configuration at NCSA that we'll be using tonight. We're going to be working tonight with a Cray 2 supercomputer, which is hundreds of times more powerful than what typical workstations can put out, both in memory size and computational speed. And we'll be working with an UltraNet, which is a gigabaud network, and a frame buffer that can display images from Cray memory at sustained rates of 98 megabytes per second. That'll be one of the configurations we'll use. Another will be an Alliant VFX80, which we've used as an effective tool for 3D interactive visualization in the Rivers project. And I think at this point we'll try to bring Illinois back into the picture here. Okay, Bob? I think this is frequency hopping or something. There's Illinois. Wrong channel. There we go. Bob, are you there?
Yes, I am, Larry. Greetings from Illinois.
Great. This is Bob Wilkinson. He's the research scientist. Bob is the research scientist that was the group leader on the 3D thunderstorm that you saw in the film and video show last night. What's really interesting is, Bob, over the last
5 years that you and I have been working on this with a lot of other people, just to see the transformation of the way that we do science in this country. I mean, as a result of the National Science Foundation initiative, the 5 supercomputer centers now have over 10,000 users on, in say, 200 universities that are linking from their desktop computers across the NSF net to these supercomputer facilities like you see here in our machine room. Okay, so we're going to use the same sort of technology you see on the evening news where you have a remote link, and we're going to use that to beam the images across in video. What do you say?
Let's do it. Let's go. We prepared something special here for Siggraph in Boston, and we thought you'd like to see it. Would you like to see it?
Go for it. This is the field he was referring to.
What'd you think about that, Bob? How'd we do?
Well, I got to tell you, Bob, that you're now talking with Alan Norton, who is in the audience with us in this show, and he's already done it.
He has,
He used the computer, you used a physical modeling technique.
Is that right?
That's right.
Well, let's move on to see how a scientist might access a supercomputer from far away. Okay, Dave McNabb at the front workstation here, who has developed a lot of the River software, is going to assist me. He's running a user interface on this Sun workstation right here. This interface is controlling the Alliant VFX80, where this animation is going, and Dave can control the rotations using the space ball that he has here on the table. And maybe we can switch the video to full screen so people can see. This is sending the user interface packets back on the 9600 baud line, controlling an Alliant VFX80 back in Illinois. The images are then being scan converted and beamed back via satellite into the video window and onto the screen. Maybe Dave could use the color slide bar to show you the manipulation of the color map. This is all going on in real time. The full rendering, science mappings are all happening on the Alliant in real time. Okay, thanks a lot, Dave.
Here with us tonight is Donna Cox, who I think, as many of you know, is a director on the Siggraph Executive Committee and is someone who has advocated collaboration across disciplines for many years. Donna, do you have a few words to say?
Certainly, thank you. Well, Siggraph has historically encouraged and supported frontier technologies, and that's what we're doing here tonight. We, in this last week, have really raised our awareness as to the potential of what a network, a high-speed network, would provide and how it would advance science, interactive visualization, and interdisciplinary research. In fact, Siggraph as a whole will be taking a larger role and playing a more aggressive role in national policy issues. And here to my right is Michael Norman. Hi, Michael. NCSA research scientist in astrophysics and one of my favorite collaborators at NCSA. Michael and I formed a Renaissance team to create this familiar image. This is a simulation of an astrophysical jet that could be 1,000 light years in length in intergalactic space. Take it away, Michael.
Thanks, Donna. Tonight I want to talk to Bob Williamson. Hey, I saw your thunderstorm simulation in the graphics theater last night. First time that I'd actually seen it, even though your office is 2 doors down. But you know, some things never change.
I guess not.
And the part that really captured my imagination was those little twisters, those little twist ties that you use to measure the rotation of the flow. I think I could really use those in my work in jet simulation.
Well, I'd be happy to share those with you. Would you like to take another look at it?
Yeah, if you got that videotape handy, could you just pull that out and fast forward to those things?
Oh, I think we can handle that. We'll have to move that along a little faster.
Go ahead.
Here we go.
Interactivity.
So what are you doing there, Bob? Why are those ribbons twisting?
They're twisting because the air has a rotational component to it as it rises, and the faster that twist is, the faster the air is rotating around its path.
Oh, that's great. I think I could really use that in my research. Have you got a couple of minutes? I'd like to tell you what I've been doing.
Yeah, I'd like to hear what you've been doing.
Well, I've been working with a group of radio astronomers, Fred Lowe, Neil Colleen, and Bob Salt sitting to my right, to look into the center of our own Milky Way galaxy for evidence of jets squirting out as they do from hundreds of other galaxies. We're using the Very Large Array Radio Telescope in southern New Mexico to probe the inner light year of our galaxy and map that region. Now what you see here,
Right behind you.
right behind you, is in fact the raw data as it comes out of the Very Large Array. And what we need to do in order to turn it into a useful image is about 10 billion floating point operations, removing side lobes, cleaning, transforming back into the Fourier domain. And what you're seeing here is this happening in real time on the Cray 2. This takes a matter of seconds, which would normally take days, hours or days on smaller machines. Now I can see that, in fact, we've made a mistake on an input parameter. The image is starting to break up into little blobs.
Yeah, I see that here too.
We're going to have to kill that job. Bob, would you kill that process and restart with a lower gain parameter?
That's the beauty, of course, of the supercomputer is that that mistake would have cost hours to days of time on, let's say, a workstation like the Sun's here.
Here we go. Okay, we're starting over again. We're deconvolving, transforming, image processing, and the image is coming into focus. And what we've discovered here is a bizarre pinwheel of glowing gas about a parsec across in the center of our galaxy. So what I'd like to do next is simulate this on the Cray 2 with a three-dimensional magnetohydrodynamics code. And for that, I would need some interactive tools to investigate the flow field. Do you have anything that you think I could use?
Well, we've been working over the last few years on various tools, and I can show you one that we've been working on recently to give us some interactive ability to look at some storms. What we have here is a storm during its worst stage. We're looking at the structure of this storm, and we're moving around it here in real time. Here, we've added a ribbon, and this ribbon characterizes the motion of a weightless particle that's moving through the air in the vicinity of this particular storm.
How do you move that ribbon in three-dimensional space?
Well, we basically are able to move the ribbon under spaceball control. The spaceball allows us to immediately change the position of the jack, and there we can see how the flow pattern changes very dramatically, moving only a small distance.
That's great.
That's exactly why you need an interactive tool.
It is. We can also trigger off our own little balloons in which we can then track air going in various different places, again illustrating the upward movement in the storm and also indicating that a lot of the air is moving downward here.
So those are just test particles, Bob?
These are just test particles. You can place them anywhere within the domain and trigger them off as often as you want.
Well, thanks a lot, Bob.
Okay.